I'm sure we will have excellent scientific contributions from your group in the years to come. You have an excellent friend, very nice family. Life is smiling at you. We are very happy this conference. I understand. We understand you are German, but we believe you are. You have a Mexican heart. So I was looking at the scientific program, and we have very, very interesting contributions. I wish good luck to all the participants. Have a very nice conference. And I would like to ask to Professor Eduardo Gomez if we can move on with the first talk of this morning session.
Okay, hello, my name is Eduardo Gomez. I would like to join in congratulating Jürgen for his 60th birthday. They say that it's a new 20.
Gracias, Eduardo.
And also, just as Guirado is saying, we're always very happy to have Jürgen in the institute. Every institute that respects itself must have a Jürgen in his faculty, so we're very happy to have one. Well, with that, I'll proceed now to introduce Dr. Stephan Paul from the Technische University in München. Dr. Stephan Paul is, his areas of research is hadronic matter and the particle physics with neutrons. He studied at the Bonn University and received his PhD at the University of Heidelberg. He was professor at the Max Planck Institute in Heidelberg, and he has participated in projects in CERN, in the KEC, the Japanese Research Center, the MLC in Garching, and the ILL in Grenoble. Sorry, I'm not a particle physics guy, so these names are a little bit complicated for me. So,
but you are very close to particle physics.
Well, yeah. So, Dr. Stephan Paul, thank you very much for joining our fest, and please take the microphone. I'm sorry, we cannot hear. They silence the microphone. We still cannot hear.
Yes, but now you should be able to hear me.
Okay, perfect.
Okay, well, it's a great pleasure to have been asked to give a presentation at Jürgen's 60th birthday. And of course, it's not a normal talk. By no means. It's sort of a little review of the time I had the pleasure to spend together with Jürgen at CERN. And so we are back to the late 80s of the last century, of the last millennium. And those were sort of different times also at CERN for various reasons. The experiments were typically smaller. And we had been in a very luxurious position that the groups from the various institutions which participated in the experiment were all residing at CERN. So it was really the time when the collaboration was at the same time a very big family, which did not only spend the days together, but also the evenings, partly working, but also partly with the families, partly barbecuing on the Jura, on the mountains, or going swimming. So it was basically day and night together with this family. And it was sort of a unique time, I think, for everybody who enjoyed CERN in the end of the 80s and the 90s. And I'll just give you a couple of impressions on the work which particularly Jürgen has done during that time. So the experiment we were all working together with called W89. It was one of the technical acronyms. It didn't have a beautiful name, but WA means West Area, and 89 was just the serial number. And the experiment was located at what was called a multi-user facility built around a big superconducting magnet, which was the Omega spectrometer, which had a field strength of 1.8 Tesla, which was very large and a very large opening. You could basically stand in the magnet. And the fringe field of this magnet was very impressive, such that you could basically not operate scopes in the near vicinity of this magnet. And even in the counting huts, the pictures of the scope were all sort of tilted. And you were also not allowed to get close to the magnet with any sort of tools, because these tools would be dragged into the magnet and potentially destroy wire chambers. And this was not only something, a potential danger, but this is something which actually happened. Safety measures were more relaxed at those days, and people were just sometimes too lazy to ramp down this big magnet, because it took quite a while with such an impedance that people said, oh, I just need to fix one screw. And off went the screwdriver right through the wire chamber into the magnet, where a number of other wire chambers, which you see in the screen, were located. And so the damage was very serious at the time. Now, downstream of the spectrometer, of this magnetic spectrometer, you see in a red square the drawing, or the circumference of the instrument, which is, it was at Jürgen's heart, namely a ring imaging Cherenkov detector. Such a ring imaging Cherenkov detector, in particular the outer part, was existing before WA19 started, but it never really worked. And it was the big achievement of the Heidelberg group, and in particular of Jürgen, to turn this instrument into a workhorse of this WA19 experiment, which allowed to identify the various particles crossing this detector. So the instrument was at those days rather long. It was what we call a forward spectrometer, where you see on the left side the target area, something like 15 meters downstream of the magnet. And since this instrument, the experiment was basically looking at long-lived particles like lambda or K zeros, which typically had flight paths of several meters before the decay. That was what was called the decay region. And that's what also was marked. But I will really concentrate on the ring imaging Cherenkov detector, and I will not talk much about the rest or what we else did. So the experiment was proposed in 1987. And you may, the one or the other of you we may see a couple of names which he still remembers. Walter Boyce was the head of the instrument. Bernard French, the late Bernard French, the late Werner Boyce, the late Fritz Müller, they were all at CERN operating at this facility. Leo Rossi is, of course, still well known in Italy. Then we had the group, my own group, where I was part of, from Heidelberg, which was led by Bogdan Poch. And then there was a group by the University of Heidelberg, which was the group of Heinze. Heinze was sort of the inventor, co-inventor of the drift chamber. And Hans Siebert was working in it as what nowadays you would call more junior professor. And Jürgen was already in the young age part of this group and signed this proposal, so which was subsequently approved. And we started data taking, the first data taking in 89 and went until something like 1993. At facilities, you always had a couple of weeks per year, not continuously. Now the instrument is shown here. And on the right side, you see basically the artist's view of the old ridge. It had quite some dimension. It was 4.2 meters wide and was quite long, and had, as you see on the left, a series of high-tech mirrors in the back, which almost has astronomical quality. And in the front, you could see wire chambers, which were supposed to detect the photons, which were Cherenkov photons, which were reflected by the mirror system. The photosensitive wire chambers were crossed by the charged particles. So you would not only see as a signal the impact point of the photon, but also the impact point of the charged particle. These photon detectors were had the technology of multi-wire chambers, but filled with a particular gas, which was TMAE, which was a photo absorber. And this was something which was difficult to operate and was a headache. So once in operation, you see what every ring imaging Cherenkov counter should tell you, namely rings. And although nowadays you have many ring imaging Cherenkov counters will produce signals, but they are not rings at all. In particular, if you look at the time of propagation detector from Bell 2, or if you look at the Dirk from Barbar, they give very complex pictures. Those gave very simple pictures. You get the rings. You have typically, let's say in the best years, we had 17 photons on average on the ring. And the crosses mark the impact points of the charged particles. Now, owing to the optics of the system, the impact point of the charged particle is not at the center of the ring. The position of the ring just depends on the angle of incidence of the charged particle with respect to the mirror system. And so on the left and on the right side, you see such rings, and you see the reconstructed momentum indicated on the bottom by the various rings, particles, which are connected to the rings. Now, of course, the one thing people had done in the past before we started was to take the rings and to fit a radius. And then you get the size of the ring and, the refractive index, and then you basically get the velocity and the type of particle. Now, that is far too simplistic because you throw away a good part of the information, which is hidden in these pictures. In these pictures. And so it was sort of a method which was invented with W89 with this experiment to use the full information and to build a likelihood which did not only take into account hits in the wire chambers, which were likely associated to a signal, but also those to background. And so the full information which was present, including the knowledge on statistics, was used to perform likelihood calculation. And then the type of particle was identified by what we call a ratio of likelihoods, namely the likelihood for particular particle hypothesis divided by the maximum of any other hypothesis you could think of. So this was a very powerful tool still used nowadays in many of these ring imaging Cherenkov detectors. And on the right side, you see a rather simplistic effect of having such a ring imaging Cherenkov counters. You see sort of the ring radii for protons, kaons, and for pions, and you can see how you can distinguish between the different particle species. Yeah. It should be noted that riches had been developed by Tom Ypsilantis and Vasigino and had been operated in test beams and had been tried in various experiments, but none of them had really worked sufficiently well to be used in a physics analysis by any of the experiments they were employed in. And this W89 Rich was the first one to prove that this technology was actually mature. But of course, a lot of work had to be done in order to turn this instrument into a reliable particle ID system. Now, if you want to get an idea of how well this instrument works, you basically count the number of photons around the hypothetical center of a ring. And then you get sort of a radius, which gives you the refractive index, and you get the numbers of photons per ring, which gives you a quality factor for this detector. And this is something which was done by Jürgen. These were famous N-1 plots, which basically covered the wall behind his chair. And for every one we took, we got new N-1 plots, every one, the next one always more beautiful than the previous one. So N-1 plots were the daily business of Jürgen for a long time. Jürgen spent a lot of time getting the instrument running itself, getting the electronics running, getting the noise reduced. So there was a lot of hardware and a lot of patience before this picture would actually emerge from all of this. Now, there were, of course, Jürgen was not alone. There were many people performing the PhD thesis. Performing the PhD thesis. And this is sort of a picture of the number of PhD theses resulting out of this experiment. A couple of these theses were colleagues of Jürgen from the University of Heidelberg and also performing work on this ring imaging Cherenkov detectors. Now, at some point in 1992, Jürgen finally finished his thesis work and he submitted his thesis to the University of Heidelberg. And that's what you see on this slide here. You can, whenever you hear Jürgen speaking, whether it's German, English, or probably also Spanish, he cannot hide. He cannot hide his origin being from Stuttgart. And so he has exported his southern dialect to the various languages. And I wonder how many people in Mexico now speak Mexican or Spanish with a Stuttgart accent. So Hans Wolfgang was his thesis advisor, and you can see the content of his thesis. The content of the thesis, which was mostly devoted to this ring imaging Cherenkov detector. But of course, this instrument wasn't built just for being beautiful, but it was built to look for an existing, hopefully existing, but at the end, a hypothetical particle, which was called the U-da baryon. And so in his very last chapter, he actually gave a first result for the hunt of this U-da baryon. That is what you see here. The motivation for this experiment actually in part came from a statistical upward fluctuation if you take a mass spectrum and you take lambdas and antiprotons and the number of pions. And on the left side, you see the teaser, which was the result of a previous experiment. And where you see the straight line, that is supposed to be the background, and everything above was supposed to be signal. Now, this picture tells you quite something about the times. First of all, it tells you that the statistical methods were not as elaborate as they are nowadays when you look for Higgs or other particles. It also shows you that you need 3 sigma or 3.5 sigma to propose a new experiment. Now, on the right side, you see the plot from Jürgen's thesis. And again, you see where you would expect a signal taking for granted the results from the previous experiment. Now, although the statistical accuracy was higher, and certainly the performance of the detector much better, the significance was still only 3.5 sigma. So at the very end, we could never prove the existence of what was called at those days the U particle, the U 3100, meaning a mass of 3.1 GeV, accidentally coinciding with the J psi mass. So this was a hunt, but basically a hunt for in vain for something which probably doesn't exist. As is characteristic nowadays, people hunt for everything which doesn't exist. Now, like every good work, this is also done by teams. And so you see here a picture of at least a part of the team which contributed to the setup, the running of the experiment, and the analysis of the experiment. And you see the square, the red square, that's Jürgen's head. And I enlarged it a little bit on top. And accidentally, I was sitting next to him. So those days, I was certainly looking much younger. Jürgen hasn't changed so much. And I think the picture on the left side is extremely typical for Jürgen. This smile, this laughing, this enthusiastic person, scientist who's there, that is how we all remember Jürgen, and that's how you can recognize him easily when either he enters the CERN canteen or wherever he is. That's sort of a branding of Jürgen, this bright smile and enthusiasm on this. Now, of course, we have also taken pictures outside. And again, you see Jürgen sitting in the grass. And there are a couple of other scientists who are still active nowadays. We actually see one of the guests of honors, which is to the left side, a little bit above Jürgen. That's Sergei, who also joined the video fest here today. And on the right side, you see the crew, which made up again this W89 experiment. And a couple of those days, very young looking scientists are now senior scientists at various international laboratories. So Bob Michaels or Eugene Chudakov are senior scientists with JLab, for example. So this is sort of one of the few slides where Jürgen must have been somewhere else, or he has taken this picture. But it was one of the few slides where Jürgen, where Jürgen was not on, but a couple of other scientists were. On the left side is Prof. In the gray jacket, it's Thomas Walcher, professor, former professor in Mainz. Lakritz, muss ich gleich. So after Jürgen finished his work in Geneva, he went on and he passed on. He actually had become one of the world experts in ring imaging strength of detectors. He had participated in the first conference on ring imaging strength of detectors, and I think he has been to almost all RITS conferences since. And so his natural path was then to join sort of the big brother of the WI9 experiment, named the SILEX experiment at Fermilab. At that time, it was running at a high-intensity proton beam, which was called Proton Center. And the pink object basically gives you, it's sort of a 10-meter long, I think it was 10 meters, ring imaging strength of detectors, which avoided the complex operation of multi-wire chambers filled with TMAE, but used photomultiplier instead, which had the big advantage, you turn them on and it sort of works. Now that is now somebody else who will talk about his times at SILEX and at Fermilab. And I would like to slowly come to the end of my presentation. Jürgen has many merits. He has an excellent knowledge of detectors. He is knowledgeable in hardware, in electronics, and in data analysis. He is very fast. So whenever there's a problem, Jürgen jumps, runs down, and basically fixes the issue. He certainly addresses the issue immediately. So he is a very fast worker. He has, I think, great enthusiasm and is full of initiative. Whenever he has an idea, he starts it right away. He has done an excellent work on the analysis also, in particular including hardware-related performance studies of this Cherenkov detector. He has excellent programming skills. And in the old days, people remember that you didn't have PCs or anything like that. They were working on a big system, which was called CERN VM. That was sort of a dinosaur of the computing times. And mastering CERN VM was quite its achievement. And then we switched to VEX or to microvexes and had first farms of microvexes, which he also knew how to operate very efficiently. He was a very good supervisor for younger students. He was the first PhD student working on W89 in his group. And there were many more which were working together with him and, of course, partly also supervised by him. I think everybody who knows Jürgen knows he has high social skills, which means he knows how to spend time and how to deal with people also outside the experimental halls. Yes, I mentioned his excellent knowledge of Southern German, the Schwäbisch, and his skills to export this to other languages. I have a very high estimation for his personality because during the time he was in Geneva, he had to withstand tragic accidents of an amplitude which not everybody is able to digest. And I really admired him a lot for having gone through these very difficult times. Jürgen, despite of this, has stayed a very cheerful, communicative, and enthusiastic fellow. And with this, I would like to wish you, Jürgen, happy birthday to you and go on for many more years to come. Thank you for asking me to give this lessons here to you.
Thank you, Stephan. That's a very nice talk. Very nice remembering photos, ideas we had, plots we made. Yes, this was very enthusiastic times. Yeah? And the photos, yeah, people. There's also Dario Barberis, who is now the big computing guy in Atlas, for example. Yeah? And you see him permanently in the same restaurant. Yeah. Yeah, very nice. Thanks a lot.
So those were the first days of physics you were doing, and the start of your career. Very nice to see how things go.
Yeah.
Yes, so I also thank you. It was very nice to see the beginnings of the career of Jürgen, and it's fun to see that after 30 years he hasn't changed his hairstyle. So that's
no, this has stayed the same. Jürgen hasn't really changed much at all. So,
what do you mean? He still has hair.
Unlike some
yes.
others, Peter.
Some more than you, Peter.
All one can do is laugh.
So I don't know if
No, it was very nice. I see the pictures. Sergey is still young, yeah.
You are still young. I was young. Yes.
So about okay, I have a question. We have an opposite, completely opposite way of fixing problems in Mexico and in Germany. You mentioned that Jürgen had this ability of fixing problems, but I was wondering whether it was the Mexican style or the German style. Let me just explain the Mexican style with an anecdote. During the World Cup that was in Mexico, there was some problem with the net, and was that in Mexico? No, it was in another country, but Mexico was playing. Jürgen
it was in the United States.
There you go. Yes, in the United States. So they kicked the ball, and the net was destroyed, and this was unacceptable because you need to have a working network in order to play. And so one of the Mexican players just went into the net, made a nut, and kicked the ball. Let's continue playing, right?
Yeah.
And this was of course not acceptable for Americans, right? So they brought a huge crane that took the goal, remove it, and then put another goal in its place. So I'm just trying to emphasize the difference between fixing problems. So I wonder, is Jürgen's style at fixing problems the German style or the Mexican style?
No, I think whenever the type of problems you had to fix were of course numerous. But if you have a new type of detector and something doesn't work, at first you certainly do it the Mexican style. Now, there's always a danger if you extrapolate such a style 100 times that it might not work. So at that point, he switched more to the German style, and then, of course, there were serious German colleagues like Peter Lennart, who was one of the fathers of this chamber, and he would not have allowed the Mexican style to be done to his chamber in a broader scale.
Thank you. Thank God.
By the way, I would like to thank Sergey, who is still here, because he is residing at CERN, and he provided me with all the pictures which were lying in my drawer of my desk at CERN. And I hadn't been at CERN for a year. So Sergey just scanned it and made them available for me so I can put them into these talks.
There are much more.
Thank you.
Yeah, much more. I will be at CERN in 3 weeks. So I will come and see you.
Call me, please. Yeah.
I hope they let me in.
I also hope. Now it's all these measures are getting softer and softer. So hope to see you. Yeah, great.
Yeah. Okay. So this was really nice. How is Prof doing, Stephan? Do you know?
I didn't see him for 2 years now. So at that time, obviously, he grew quite a bit older. He is getting to his 90s. And he gave up playing golf. He has a knee problem, and I think he was getting close to 90. That's a serious age, and he doesn't show up anymore really at its institute as much as I know.
You know, Prof is very famous in Mexico because I use his book to teach nuclear and particle physics.
Many people do. It's a very successful book.
Eric will know the book, yeah?
I use it now.
You see?
Yeah, I teach with that book.
So Prof was also in the committee of my thesis defense. So okay.
We have a very nice scientist in the conference. Hi.
Pregunta al frío. Yeah.
So do you want to take a break and we reconvene at 10 and 11, sorry?
Okay.
All right.
So who wants